So we started off basically being interested in the tunneling problem, looking at statistics of escape rates. And I think we found that there are some interesting issues that come up there that might have something to say about the wave functions themselves. Okay, so I'm going to start off by motivating where this work comes from with regard to tunneling, and then basically try to outline what we think is interesting from the point of view of wave function statistics or other properties of chaotic wave functions. Okay, so as a sort of a basic motivation for what we're doing, Niall and I started working a number of years ago on issues of tunneling in multidimensional systems, where we basically try to take standard tunneling problems. One of them might, for example, be where we'd like to calculate semi-classically resonances. Okay, so I'll take a very simplistic view of a resonance, that it's, in an approximate sense, the stationary state of the wave function. It's unnormalizable, but reasonably confined to, for example, a potential well. And escape basically means that we can find solutions like this with outgoing flux at slightly imaginary values of the energy. Now, we're interested in problems where these resonances are associated with tunneling, so these gamma n's are very small. Okay? So in any sort of physical system where you've got this sort of effect, they're going to be interesting if you've got some degree of complexity in your model. And anytime you've got complexity, what you should do is a natural sort of approach is to start using statistical modeling based on random matrix theory to sort of understand it. This has been used in the past, for example, in these sorts of models. And I'm going to just mention two particular references. There are others, but in the context of molecules, basically associating random matrix models with the internal dynamics in here, and then modeling the coupling to the outside, giving distributions, was used in the context of reaction rates or dissociation rates by Miller and others, and then there are other references in that field. And it's also been used in the context of conductance peaks through quantum dots, which are also governed by tunneling type effects. Okay? So the standard thing you're going to do basically is say, I've got a complex system, it's going to couple to the continuum, and then given a sort of model of coupling to the continuum, how do I derive distributions, how do I understand the statistics of what's happening in the tunneling rate? We got into this because we were sort of interested in looking at simple models or simple ways of understanding these sorts of tunneling effects in relatively low-dimensional systems, but systems which are non-integrable or chaotic. And then you might naturally ask, well, lots of systems have random matrix type behavior which are not low-dimensional chaotic problems. Okay, so can you, for example, see signatures that are non-universal in statistics? That might tell us, for example, in the context of quantum dots, whether or not when we see random matrix theory, it's due either to the fact that we've got a simple low-dimensional chaotic problem, or it's a horrible mess with interactions and things I don't claim to understand. Okay, so if you can test these sorts of effects, it might give you an understanding of how well you sort of can model these sorts of problems. So I must, at this stage, sort of make a confession, which is that all of the physically interesting problems, I imagine, have to do with lifetimes and potential wells. So if I was to think of a one-dimensional model of this, I might imagine I've got a one-dimensional potential well with a potential which looks like this. So if I solve only very approximately, I'm going to find basically what look like discrete energy levels, but if I look at those more closely, I'll find that actually these correspond to resonances, and I might try to understand them properly by trying to understand a resonance width here, okay? We'd love to be able to model problems like that, but it turns out that we're poor enough numerically that we prefer to do a slightly different problem, which I'm going to just assert works in exactly the same way. So a similar problem is that I'll take a double well potential. Once again, if I solve the problem only approximately, I have what look like discrete energy levels, which in this case are degenerate if I've got a symmetric double well, but if I resolve more closely, I'll find that there's a doublet, and in this case I'll look for a splitting delta En. Okay, so in any of these problems, you can have basically approximations based on WKB, where you basically look at a sort of tunneling action to cross underneath the barrier. There's a standard WKB formula. So I could write as a function of any parameter such as energy, if I just basically plot the scale of what's happening here for the splittings or the resonance widths, normally you would get some formula. Let's concentrate on the notation of resonance widths for the moment, which would be of the form in amplitude times a decaying exponential. Okay? And in one dimension, that's all there is to do. Okay? You don't do anything beyond that. What's interesting about complex problems, which in the context of this talk will mean two-dimensional problems, but in principle higher dimensional issues, is that while a formula like this will govern the sort of mean behavior of the tunneling rates, be it resonance widths or splittings, you'll actually find that you'll have random behavior spread around this sort of mean behavior. And you might expect that if this dynamics inside this well is chaotic or non-trivial, then these, the distribution of these tunneling rates about that mean behavior might be non-trivial. And in fact, you find that it's sort of governed by quasi-statistical models. Okay? So that's the sort of analysis that was done in the context of reaction rates or conductance peaks and quantum dots. And we sort of got interested because we had what we thought were reasonably simple models of these tunneling rates using simple models of dynamics, basically complex trajectories crossing the barrier. So we applied what we were doing to that, and we got results that work reasonably well. Okay? So this is our version of what random matrix theory tells you. So as I said, I'd love to present results for resonance widths, but they're hard numerically. So in doing numerical simulations, we do double wells. Okay? It works in exactly the same way. There's nothing fundamentally different about the distributions. And then what we can do is basically take any given resonance width or a splitting and scale it by the mean behavior given by a formula of this sort. Then we'll get something which is basically scaled so that our variance is 1 and so on. And you get models which work fairly well. Okay, so here's a two-dimensional potential well. This is basically a histogram of the energy level splittings computed numerically. This dashed curve is the Porter-Thomas result, which basically applies if you're just saying the tunneling rate is the value of the wave function at one particular point. And you, in general, get sort of a different distribution, which is well described by the theory I'm going to go into a little bit more about later. Okay, so it seems to work quite well. Yeah?
Is this above or below threshold?
It's below threshold. Okay, so everything I'm talking about works if the energy here is below the saddle energy. In fact, what you can see is, I'll go into this more later, every time I present one of these diagrams, you see a little red dashed curve here, which is actually a complex orbit traversing the barrier in imaginary time, connecting to a real trajectory shown in green. Okay? We tend to show fairly short trajectories crossing the barrier simply because numerically, if we want to generate lots of double wells, if we're too far into the barrier, the splittings get small very quickly. It's hard to compute them numerically. So simply to get good statistics, we tend to choose the energy fairly close to the barrier, even though that's not really an important issue. This has nothing to do with what I want to say, but it's an amusing example, so I'll just show it. An interesting expectation we had when we were looking at double wells is that you've always got positive splittings, which mean that the odd eigenstate is always at higher energy than the even eigenstate. Turns out that this is true if you've got a symmetry which is reflection through an axis. If you've got symmetry which is reflection through which is in reflection through an origin or inversion in the xy plane, then it's true on average. Most of the splittings are positive, but the distribution is actually allows you to get negative splittings, where the even state is at higher energy than the odd state. Okay? Interestingly enough, this is something, if anyone has a solution to this, I'd be interested to know. This comes out naturally from the models we use, but these are semi-classical. I don't know an exact quantum proof of why this should be so, why you should always get positive splittings in the case of a reflection through an axis. Because clearly, in this case, there's no fundamental reason. It depends on the symmetry. Okay, so it seems like everything works. However, in lots of examples, it doesn't. And in fact, the very first example we tried out our methods on, it failed miserably. Okay, so the first example you might try would involve a problem with a symmetry. Here we've got a problem with a symmetry in y as well as in x. You've got a tunneling orbit along the x-axis, and it connects actually to a periodic orbit along the x-axis here. Here's the calculation we dutifully do using our theory. Here's the numerical example. They've got nothing to do with each other. Okay? So clearly there's something going on here. The distributions I wrote down just using simple assumptions of random matrix theory just don't work. Okay? So what's the possible reason for this? Well, you might think this is because I'm looking at statistics. I'm going to explain later that our model basically models the tunneling rate by sampling the wave function on this green orbit here. You might think this orbit is on a symmetry axis. That might be an effect. Well, it's actually got more to do with the fact that it's a periodic orbit. Okay, so I can compute a different potential well, which has no symmetry in the y direction, but I'm going to tune parameters here so that the complex tunneling trajectory connects onto a periodic orbit in real dynamics. And here, once again, we find a strong deviation from the basic assumptions of random matrix theory. Okay, so this is the theory we dutifully construct. Here's the quantum histogram. And unfortunately, in both cases, it looks more like Porta-Thomas than anything else. And the whole point of what we were doing is to sort of emphasize that it wasn't Porta-Thomas. So this was sort of disappointing when we found them.
Just one question.
Yeah?
So from this trajectory, you're getting many different quantum states.
Yeah. There's something I'm sort of finessing here, which is that if I change the energy, generally the trajectories will change. Okay, so if I look at a spectrum like this where I vary energy and follow splittings or tunneling rates, the orbits are going to change, so the distribution will be changing. What we've actually done here is we've kept energy fixed, and we've asked what values of h bar have energies at this energy. And then we get splittings in h bar, but it's sort of the same thing.
So you're always looking at the same kind of quantum.
Yeah. So in all of these ensembles, we're keeping the energy and all of the classical structure completely fixed. Okay, so there's an obvious explanation from this, which luckily had, appeared in the literature not too long before, which comes from Kaplan and Heller, okay, which basically states that, well, if you look at wave function statistics on a periodic orbit, they've been able to show that you get very strong deviations from the simple Gaussian assumptions of random matrix theory, okay? And you can basically then argue that this is a very feasible explanation for these deviations. So the statement is that basically if this tunneling trajectory here connects to a generic orbit, then the simplistic model from random matrix theory works. If it connects to a periodic orbit, then the tunneling rate has to do with the properties of the wave function on a periodic orbit. And Kaplan and Heller tell us that those are non-generic. We need to be a bit more careful. Yeah?
What exactly do you mean by connect?
Okay. I'll go into this in a little bit more detail later, but it is an important point, which is that if we look at this red trajectory here, it's a periodic orbit with an imaginary period, just like we heard about last week from Bill Miller. It's basically the instanton orbit. Any instanton orbit, it's going to have, well, in this case, you see a turning point where the momentum becomes zero. Well, in that case, the momentum is actually real. So normally the coordinates along this red trajectory are actually complex in phase space. At the turning point, they're real. So instead of carrying on in imaginary time, there's nothing to prevent me from going in real time and generating a real trajectory. So in that sense, they're actually parts of the same trajectory if you look in the complex T-plane. Yeah?
I was going to ask, does it matter whether the orbit is stable or unstable?
Yes, enormously. You can do a lot. I mean, the stability here refers to the green real orbit. Yeah, you get very different behavior depending on whether or not it's stable or unstable. We're going to assume that we've got basically chaotic dynamics in here, so we're going to assume instability. I can bore you for hours about stable orbits if you want, but I'm not going to talk about them here. Yeah?
I just wanted to understand, you always talk about one orbit, but shouldn't there be many orbits which contribute to this energy balance?
Okay, there's one orbit which is important for the tunneling rate. Okay, because actually we can compute, lots of orbits crossing the barrier, but because you get penalized by an imaginary action, there's basically one which minimizes the action. The properties of the wave function inside the real well, and basically if you ignore tunneling effects, the statistics and so on of these levels are determined by all of the real orbits inside here. So that's an interesting question. How do these connect to the complex orbit? I can bore you for hours about that if you want to, but I'm not going to talk about it. Okay? So what our point of view is, doing quantum mechanics in this well, it's a chaotic problem, so it's a hard problem. We're going to basically try to use, if possible, non-semi-classical models for that, such as random matrix theory and so on. And the semi-classical analysis comes in basically into formalizing what happens with the coupling to across the barrier. Okay? Everything else, in principle, might be done quantum mechanically. Okay, so in order to understand how these deviant wave function statistics on the orbit might have an effect, let me give you a basic idea of what the structure is. Okay, so how is it? How do we connect, basically, given a wave function here, how do I determine what the tunneling rate for it is? Okay, so there's a very simple semi-classical model for this. And now, this basically uses the idea of using complex orbits to compute tunneling. It's been going on for a long time. Bill Miller was doing this in the early 70s. There's a long history of doing this. I'm not giving it an extensive literature review. I'm just saying, basically, just pointing out a few papers that led us to what we're doing. Okay, so this is basically a subset of what's happening. And the idea I'm going to talk about, basically, we sort of found in a couple of papers in the 80s by Auerbach and Kivelson and Wilkinson and Hannay. And the idea basically is quite simple. You take this red trajectory, which is an orbit which crosses the barrier in imaginary time. As we've just discussed, if I go to the end point and continue in real time, I can follow a real trajectory into the potential well. Well, you can write within semi-classical approximation a very simple formula for the tunneling rate, which says that let's sample the wave function along a section, which later on we're going to use to generate what looks like a surface of section or a Poincare map. And there is from the dynamical properties of this complex orbit crossing the trajectory, I can produce what looks like a kernel with arguments, basically S and S prime being coordinates just along this section, not in the full configuration space. And then you can derive a formula following this work, which basically says that tunneling rate is what looks like a matrix element with this simple function acting as a kernel. And the important point is that this kernel, this is just a schematic representation. It's sort of localized within an area of some sort of power of h bar around this classical trajectory. Okay, so what we're essentially doing is sampling the wave function in a region of actually phase space later on around this periodic orbit, this real trajectory, and the properties of the wave function then determine what the tunneling rate is. Okay, so if the wave function is large on this orbit, you get a large splitting or resonance width. If it's small, you get a small tunneling rate. Okay, now it's very tempting, and I'll come back to this later.
You haven't done it this way, but you assume the symmetry, so the right-hand side, it's the same wave function on the right and left. Okay. This is the sort of schizophrenia where I'd like to be doing this problem, but we're doing this problem. So in this problem, you need to assume a symmetry. In this problem, you can still construct this complex orbit. The difference is that for resonance widths, it goes back and forth, so it goes across twice. And for splittings, it goes across once and use the symmetry to go back. Otherwise, you don't really need symmetry. So this sort of suggests modeling the equation for the symmetry as being like a matrix element of some operator. The difference being that the matrix element is not in the usual Hilbert space, but on a surface of section. So I'm going to do some fairly bad boy mathematics later on where I start talking about quantizations of surface of section. Okay? But that's sort of what the structure of this is suggesting to us. So let's basically try to... since I'm building up a model involving random matrix theory, I can't actually prove anything, right? I've got a chaotic problem. I'm just going to assume the sort of Boehigas-Giannoni-Schmidt conjecture. So since I'm just not proving anything, let me go the whole hog and just build up an artificial model which has the structure of the problem I just outlined. Okay, so if we go back to this formula which expresses the tunneling rate as a matrix element, well, let's say that these states n, these wave functions, they're living on a section. Okay, let me imagine that these are states which are living on a Poincare section or a quantum version of it. So what I might think is that, yeah?
Using the first formula, it still depends on this prime, right? The right-hand side. If you integrate over
Oh, I've forgotten integration. There should be an integral over S prime too. Okay, so my model is going to be that sampling the wave function on a section is going to be a bit like doing dynamics on a Poincare section. Well, the quantum mechanical version of this is a Hilbert space. And if I want to carry the analogy even further, this might be a finite dimensional space. Okay, so let's imagine I had a chaotic map acting on, for simplicity, a finite dimensional space. The chaotic map is in the form of a unitary operator U with what I'll call chaotic eigenstates n, which are like eigenstates of a standard chaotic quantum system. Then instead of energies, I'll talk about eigenphases. Okay? And you can sort of argue in a very formal way that there's a relationship, you can build up a relationship after following Bogomolny, which says that, in a sense, this is a natural model of a mapping on a Poincare section, classically. Okay, well, if I was to basically ask what's the properties of the wave function around that classical orbit I was talking about, well, in the surface of the section, it's going to correspond to a point P node. Okay? The formula basically says that we're going to sample the wave function in phase space in some region of phase space around that. Okay? Well, a natural way or a natural measure of the size of the wave function there, which is the one used by Kaplan and Heller, is that let's just take a wave packet which is localized in phase space at this point. So for simplicity, imagine a Gaussian minimum uncertainty wave packet or a coherent state which I move to this point in phase space. You might basically then look at the statistics of an overlap of the chaotic wave function n onto this wave packet, okay, where the wave packet is localized in the periodic orbit. And this is what Kaplan and Heller do, and they build up a theory for that, which works really well and shows that scarring gives you very strong deviations from basic random matrix theory. Okay? And what's going to help us is that we're going to note that if I take the square of this, it looks an awful lot like what we're interested in, except instead of this operator T, I've got a projector onto this wave packet. Okay? So it looks very similar formally, except I'm replacing this projector by this sort of different operator T up there. But in phase space, they actually look quite similar. If I was to look at some phase space representation like a Weil symbol, they would both be localized and be approximately Gaussian around this point in phase space. Okay, so what we're going to do basically is take their work and see what we can do with it. Okay, so I'm going to give a very simplistic view, and I hope Lev forgives what I'm about to say. This is basically a very sort of brief summary of my understanding of what they do. Okay, I take full responsibility for anything that's incorrect in this. So basically, their idea is as follows. Let's suppose I start with a chaotic map U, okay, which I can project or write in a basis of chaotic eigenstates n in the following way, where theta n are the eigenangles. And basically, you know, Heller started doing in the 1980s the following thing, which is that if I want to understand properties of overlaps, let me just take a wave packet somewhere in phase space, iterate it with the quantum evolution, project back onto the initial state, giving the autocorrelation function. If I expand this in the eigenbasis, then I get something which also oscillates as a function of the time t. So a Fourier transform will pick up in a very natural way a spectral density of these overlaps. Okay, so if I can understand this, what they call an envelope function, I can basically understand something about what happens with these overlaps. Well, if I was to launch a wave packet in the generic part of phase space, of course, it's going to decay very rapidly. I'll just recover standard random matrix results that, on average, these would be equal to 1 if I normalize everything appropriately. However, if I launch a wave packet on a periodic orbit. I get recurrence, and when I Fourier transform that, I actually can show by averaging this equation that the average value in any given part of the spectrum of this square of the overlap is going to be the average part of this. And if I basically average it, I'm going to pick out basically properties of the periodic orbit itself using linearized dynamics. And you can derive a nice straightforward formula for an envelope function, okay, which basically tells me in any part of the spectrum, if I look at all of the wave functions in a small window of the spectrum, compute this overlap, project onto the wave packet, then the variance is something which depends on where I am in the spectrum in a known way. The interesting thing is that this right-hand side is independent of h-bar if I normalize my states correctly. Okay, so I get something which becomes basically deviant from random matrix theory, which says that this overlap here should always have a constant variance, and it's deviant in a way that becomes independent of h-bar. Okay, so to continue what they do, or my interpretation of what they do, well, what happens now? Suppose I look at these projections onto these chaotic wave functions. I know that the variance in any part of the spectrum is going to deviate from the value predicted by random matrix theory. So whatever distribution these overlaps have, ORMT doesn't work. So I'm going to give a very simplistic explanation is, well, what's the simplest possible distribution which satisfies this constraint? Well, the simplest possible distribution is still Gaussian, but just let's modify the variance. I'm not going to offer any explanation for this whatsoever. We just try it simply as a guess, and it works really well. Yeah?
So, instead of E, you're using another H-bar. So you have to modify this logic slightly. You're solving for eigenvalues of H-bar now. So you fixed the interval.
Okay. I've gone to a new model where I look at a quantum map, where I'm looking at a unitary operator, and I've got the standard thing where the dimension of the Hilbert space plays the role of h-bar. I mean, I've been finessing things. So, for example, here E looks like energy, but actually, if you look at this formula, it actually corresponds to an eigenangle. Blame Kaplan and Heller for that. I'm borrowing their notation. Okay. So, but it's sort of, I'm trying to get the flavor across. I'm not being very careful about the details here. But, I mean, the point is, this assumption works amazingly well, right? I mean, this red curve is what you expect from basic random matrix theory. And here, basically, this is an accumulation of the whole spectrum. If you look at the overlap, you get a marked deviation from that random matrix result. There's a green curve underneath here, which comes from this distribution. Okay, so that works really well. Now, if we go back to, it came into calculating this envelope function. So I haven't described what this is. This involves the stability properties and so on of the periodic orbit. The interesting thing also is that this is actually independent of h-bar, so this is fixed in the semi-classical limit. Okay, so if I go back to what we were calculating, if I look at this matrix T, if this matrix T was basically a projection onto a single overlap, that would actually explain everything we've been doing. So I'd hand over to Kaplan and Heller, they would explain everything else. What interests us is that actually we've got something very similar. So qualitatively it's the same, but this T matrix has a bit more structure, and this actually leads us into an interesting question. Okay, so let me go a little bit more into how this operator T differs from a projection onto a single wave packet. So what I've said basically is that it's all got to do, if we go back to the original problem, with properties of the wave function along this real extension of this complex orbit crossing the barrier. Okay? Well, if I look at, on a normal Poincare section, I've got, in classical mechanics, if I've got a potential well, I'll draw a section, for example, by fixing a configuration space coordinate. I've got a sort of standard Poincare section mapping defined by normal real dynamics. It turns out there's a second mapping I can construct, which is completely independent of that, which is a bit strange, but what I'm going to do is take this crossing complex orbit. I'm now basically taking an evolution which says, evolve here for some real time until I get near the barrier. If this point is sufficiently close to this crossing orbit, if I now continue with imaginary time, I'll go around the barrier and come back sort of somewhere close to real configuration and phase space. And then I'll undo that real evolution using a negative time evolution. So my contour in the complex plane does something like this. So in a sense, if there weren't any singularities here preventing me from doing it, I could just start at this point, do an imaginary time evolution, go out and come back. But that worries me because I might sort of be looping around singularities. So I'd basically start close to this orbit in phase space, and then nearby, by going along a contour like this, I can define a mapping which is complex. So this is a symplectic mapping which is complex. That doesn't stop me from quantizing it. Okay, so I can construct an operator which is the quantum mechanical equivalent of this symplectic mapping.
It's the usual story. I mean, why don't you keep time real and be in a complex phase space rather than complexify time? Because this is not going to work in higher dimensions. I mean,
It does.
always. I can keep phase space real and just use a matter of time.
Oh, you don't keep phase space real. What you the phase space is going to be complex. If I start with a real initial condition here, if I go along this trajectory and come back, in general, it'll be mapped to a complex image point. So actually, it's a Poincare mapping on an analytic continuation of the Poincare section.
So both time and space have to be complex.
Yes.
And this is full phase space on Poincare section.
On the Poincare section, it's still complex.
Yeah.
The only thing that's real, well, energy is real. And if I fix a Poincare section by saying the x-coordinate, for example, is equal to 0, then that x-coordinate is real, but all the other coordinates are complex. Okay, so if I look at what's happening here, I basically then say that this operator T, you can interpret it basically as a quantization of this complex surface of section map. Okay? It's like a unitary operator, but not unitary because time is complex. So, as I mentioned before, as I move away from this orbit in phase space, I get a penalty for having a complex trajectory crossing the barrier. So actually, if I look at a symbol of this operator, it's going to be heavily concentrated around P naught. So the simplest thing we can do, and this is consistent within semi-classical approximation, is to replace the complete nonlinear map with its linearization. Okay? So I can construct a monodromy matrix, or a symplectic matrix W, which is symplectic but complex, which linearizes that dynamics. And I can construct an operator which quantizes that. And sufficiently close to the periodic orbit, this will give me a good approximation for the operator T. Basically, W, it's a linearization of motion, albeit in complex phase space. I can derive it from a quadratic Hamiltonian, so it's harmonic oscillators. Okay, so I can basically construct a quadratic normal form which will generate W, and that quadratic normal form, it's a harmonic oscillator, it's got eigenstates, so I can construct eigenvalues. And when you look more deeply at the structure of T, basically it's got I can write basically simple eigensolutions. So my operator T hat has simple eigensolutions phi k, or in this case just k with a tilde over them, and you basically get something of this form. Okay, and in fact these eigenvalues are independent of h bar.
They're complex.
They're real. They're the eigenvalues of W.
Yeah.
So the eigenvalues of W are e to the, well, it's elliptic W. Okay, the transverse Hamiltonian is nice elliptic Hamiltonian, so it's normally got eigenvalues which are e to the I omega t, but the time is imaginary. So this is these are eigenvalues. If I put a plus or minus here, I've got real eigenvalues. So it's an elliptic Hamiltonian propagated for imaginary time, which gives you real eigenvalues, but independent of h bar.
This is the tunneling. The lambda itself is just a tunneling effect.
Well, that sort of tells you how the transverse dynamics affects the tunneling rate. Okay, so if we go back to this, I now basically can write T. I know what its eigenfunctions are. They're just basically excited harmonic oscillator eigenstates. I can do an expansion of this matrix element in this harmonic oscillator basis, denoted here by K with a tilde on top. And the only difference from what we had before is that I now have, instead of T being a pure state, it's basically going to be a sum of projections onto all of these harmonic oscillator eigenstates. Okay? So if I want to go and sort of take Kaplan and Heller's work and generalize it, what I've got to do basically is ask not for the statistics of the chaotic wave function projected onto a Gaussian wave packet, but onto a whole sort of sequence of coherent states which correspond to the excited levels of a harmonic oscillator. But otherwise, it's exactly the same. Okay, so let me denote basically xk, these projections, where I'm going to be doing statistics in n, so I'll just basically regard x as something like a quasi-random variable. Well, if I want to understand tunneling statistics, I need now to understand not just the projection onto one state, but collectively all of these harmonic oscillator states. So what I'm going to do is just basically take the simplest generalization and say, can I understand the correlations and variances between these different overlaps? So I'll project the wave function onto different harmonic oscillator eigenstates, and then I can construct a model for the variance following what Kaplan and Heller do. And I can actually, yes, I can construct a matrix by averaging over the dynamical properties of this periodic orbit. And I'm not going to write it down, but you can write a matrix which depends on where you are in the spectrum, which here is suggestively denoted E. And it depends on linearized dynamics, and it's independent of h bar. And that basically gives me a constraint on the correlations and variances of these overlaps. Okay? And we compute this basically from a linearized correlation. So basically, we're going to end up writing the linearized evolution in a harmonic oscillator basis. So it turns out you can do everything here based on a few classical invariants, the eigenvalue for the unstable periodic orbit you would expect. The properties of the harmonic oscillator come in through the angle between stable and unstable manifolds. Okay? Normally angles are forbidden in symplectic geometry, but here I've got a harmonic oscillator state which gives me an inner product and it allows me to speak of an angle.
This is the complete periodic orbit, the complex periodic orbit. This eigenvalue is for the pole guy.
Okay.
That's the real space part.
The complex periodic orbit tells me what these harmonic oscillator states are. All right? Once I construct those...
That's just the imaginary. That guy is just the imaginary section, not the whole complex one. It's just a tunneling part. Because you just computed it on a tunneling.
Yeah, so the tunneling problem gives me an elliptic structure in phase space. And it's that matrix W. Now I say that this happens also to be on an unstable periodic orbit of real dynamics. So I've got two structures here, the elliptic and the hyperbolic one. And basically there are two parameters which allow you completely to characterize this geometry insofar as it's necessary for correlations.
What is the angle again?
What you do is you basically choose coordinates which turn this ellipse into a circle. And then it's the angle between the stable and unstable manifolds.
The real orbit.
Of the real orbit. Yeah. So normally that's forbidden. I'd get shot if I did that. The fact that I have an elliptic structure underneath allows me to do that. Okay. So it turns out I'm going to make the same bold statement. I'm going to now construct the simplest possible joint probability distribution consistent with these constraints. Okay, so we say I'm going to construct from linearized dynamics an explicit matrix which tells me what these correlations should be in any part of the spectrum. I don't know anything else about this statistics, so I'm going to assume that it's a normal distribution consistent with this constraint. So I just simply write this down and run for cover. Okay, and when it's accepted, we then say, well, let's see what this gives us. Well,
here I say it works, but actually these graphs at the bottom are sort of boring. All I'm doing here is verifying that our calculation of the variances was correct. Okay, so this is some numerical simulation for quantum maps. The green dots represent your actual overlaps. The histogram is the local average, and the red curve basically represents this correlation. So all we're doing here is verifying that we didn't make a mistake when we did this model using linearized evolution. What's non-trivial, and what we don't even pretend to show, is that the statistics of these green dots about this average is described by this distribution. So it turns out, however, to work really well. Okay, so for example, if I let xc_kl be equal to xk_xl, okay, if I do statistics of this, it can help me understand correlations and so on. And without scarring, these would be uncorrelated, so the average of this would be 0. Okay, so in uncorrelated overlaps here, I should expect any distribution of this variable to be symmetric. And here we find a very asymmetric solution. Here I'm looking at the correlations between the projection onto the ground state with the second excited state. It's very asymmetric, but the numerical results we get from looking at quantum maps agrees very well with the red curve, which is this normal distribution. Okay? And likewise, you can project onto the higher states, and you get, anytime you look somewhere, you'll find reasonable agreement. I want to emphasize here that even though these two results taken from different parts of the spectrum seem to be similar, their scales are very different. So the average overlaps in the scarred part of the spectrum are going from 0 to 10 here, whereas they're going from 0 to 1 in this case. So you can basically recover these deviations from random matrix theory over fairly large variations in scale. Okay, so I won't describe how, but we can go back and put that information back into a model, and we get distributions which work. Okay, so if I take the histograms I was showing you earlier, this is what we get without assuming scarring. The blue curve is what we get with scarring, and it's a reasonably good approximation to the observed statistics. Now, because the numerical calculations here are not that easy, you need to get lots of splittings, and they're numerically small and so on. We can't actually get, super studly histograms here, but this is reasonably convincing, I think, that something is correct in the result. And it works also in the case of...
You never explain the angle brackets. No, because you're not showing our cards, because you're actually you have a specific model, you're doing some Poincaré section, you're computing angle brackets on the orbits.
Yeah.
And you get the blue curve, but you never show us the intermediate.
I've got 5 minutes left.
All right.
I'll be happy to explain it. I've got transparencies. If you want to stay on after class, I'll give you a tutorial. Okay. So it works. What I want to sort of do in the remaining time is to just go back, actually. So it works for tunneling rate statistics, but it might be interesting just to examine the sort of consequences of this distribution. So let's go back to the joint probability distribution, where now we, in a sense, want collective statistics, not of projection onto one state, but onto this harmonic oscillator basis localized in phase space. I have actually sort of run roughshod over a couple of issues, which is that one thing is that the description I wrote down, I can extend the harmonic oscillator base in principle up to infinite quantum numbers. I'm using a linearized approximation of dynamics in the neighborhood of the periodic orbit, so eventually that will become invalid. And in any case, even if it was linear, if I was doing this for something where the dynamics was exactly linear near the periodic orbit, I would still worry that if I let the harmonic oscillator component go to infinity, the decays we get here are actually decaying very slowly. Okay, so as a distribution with an arbitrary number of variables, this is actually quite complicated. So what we can do instead is let's just truncate it. And the Gaussian distribution has a nice property that if I take a subset of the variables, the distribution in those is still Gaussian. And the natural thing to do with any normal distribution is to diagonalize it, to write it as a product of independent Gaussians. So let's basically, in a dumb sort of calculation, just take this symmetric matrix here,
diagonalize and see what the eigenvalues and eigenvectors give us. Well, the eigenvalues give us something here. I'm plotting as a function of the spectral parameter E. The eigenvalues give us a decreasing sequence. They have a non-trivial limit as the cutoff here goes to infinity. They actually tend logarithmically to infinity, which is telling us essentially that by extending my harmonic oscillator basis as far as I want, I can make deviations from random matrix theory as large as I want. So there is actually no limit as m tends to infinity of this distribution, but if I truncate it, I get something which has this structure. The eigenvectors, which I'm going to plot in a Hasumi representation, are also interesting. Okay, so here basically I've taken, as a function of the spectral parameter, I've selected a couple of eigenvalues in each case. So if we look at the center, for example, this is where scoring is greatest because we've got the greatest deviation from random matrix theory up here. Here's an eigenvalue, which tells us that there's an eigenvector here for which the overlap is, in general, 17 or 18 times greater than I would expect from random matrix theory. And if I look at the eigenvector and write it in a Hasumi representation, it's got the structure and phase space. Basically, it knows about the underlying periodic orbit and its stable, unstable manifolds and so on. And I can do the same for other eigenvalues. And in each case, the eigenvectors seem to be stretched out along the stable and unstable manifolds. Well, it turns out that there's a natural way to describe this, and this basically brings up calculations that have sort of appeared under various names before. So if I want to describe scoring in general in terms of representing patterns in phase space or in wave functions, then it's sort of natural to try to construct universal measures of what those patterns are like. These have come up under various guises. Scar functions mentioned by Vergini and Carlo. They've been called universal test states by Kaplan and Heller, or quasi-modes by Ford, Nonnemascher, De Biever, and others. Okay? And you can actually see very simply where this comes from, which is that correlation matrix we want to diagonalize is nothing but a sort of discrete Fourier transform of the linearized propagator in a harmonic oscillator basis. So I'll take a Hamiltonian which linearizes the hyperbolic motion. I'll then take a Fourier transform that formally in a harmonic oscillator basis gives us this matrix. So basically, by Poissonry summing this discrete series, we can show reasonably easily that the eigenvectors, or S, seems to actually just reduce to a set of projections of, these are basically eigenstates of linearized dynamics, which normally has a continuous spectrum, but we're going to pick out a certain discrete subset of them. Okay? And these become the states which gives the most natural description of the joint probability statistics. So when I show these eigenstates here, the eigenvalues don't have a good limit as the truncation tends to infinity. The eigenstates are nothing but linearized, a discrete subset in each case of the eigenstates of the linearized dynamics. Okay? So when you do that, if we just relabel them in order of decreasing eigenvalue or variance, if I can then construct from this what these sort of natural states for describing statistics, which are in phase space stretched out along the stable and unstable manifolds. And then if I look at the statistics, the projection of the chaotic wave function onto these states, I get a very natural description as a product of independent Gaussian random variables. And these are statistically independent. So, for example, if you look at this numerically, you'll see that the distribution of a product of these two overlaps is symmetric. So it's sort of evidence in support of the fact that these are uncorrelated. Okay. Just as a bit of voodoo science, since it's traditional scoring to do this, I'll just mention that these also give us a nice way of basically looking for what patterns to look for in scarred eigenfunctions. Okay? There's nothing fundamentally different here than wouldn't have been found by the other people looking at scar functions and universal test states and so on, but it's still an amusing thing to do. So here are some eigenfunctions of a cat map in a Hasumi distribution. Here you get basically at each energy, at each part of the spectrum, a specific set of these eigenfunctions which
give us a template for what to look for. And we find indeed that we can produce scarred eigenfunctions actually in any part of the spectrum, and the patterns follow the patterns we sort of predicted. If you look in the billiard, if you basically treat the boundary integral method as something like a quantum map, you can describe scarred functions on the boundary. You then continue these into the interior using the green function. And when you look for scarred eigenfunctions, you can again see the patterns that you're looking for. So here's the sort of simple, most dominant test state computed right at parts of the spectrum where scarring is expected to be greatest. When you look at scarred eigenfunctions, you tend to find a similar looking pattern. Okay, you can convince yourself that actually this isn't just something which is accumulating along the eigenfunction. You can count nodes and so on, so you get the pattern. And I would also emphasize that these are a bit less obvious, the connection between these states here, but you also get scarring even away from scarred regions. You can even find scarring in the anti-scarred regions where a Gaussian wave packet would have minimal overlap. Okay? So I'll stop there. So basically, the conclusions are that the first point is that scarring is actually can have very strong physical consequences. Okay? Tunneling rates are a reasonably physical quantity, and now they can actually be dramatically affected by scarring. And in a way that we can now basically say that we understand. I mean, it's basically more or less completely analyzed. Coming from that, I would say that we would also point out then that if we want to look at collective wave function statistics in a region of phase space around the periodic orbit, then these scar states or quasimodes or universal test functions provide a very natural basis for describing the collective statistics. And then in terms of what's coming in the future, I'll just point out that what we've been talking about so far has been for tunneling rates where the energy is sufficiently below the barrier. Of course, many interesting physical problems you want to approach fairly close to the barrier top. So we're working at the moment as to how to generalize all of this to energies where you're very close to the threshold, where you get uniformization of tunneling rates and so on. Okay, so that's basically it, and I'll stop there.
What is a splitting? In the sense that you've calculated lots of eigenvalues,
yeah,
and then you see energy differences between them. Now, a splitting would think to have something to do with the wave functions being very similar on one side.
Well, it depends. In numerical simulations, or if you're doing just models, it's obvious because the splittings are always so much smaller than the mean level spacing that and when we've been doing our numerical models, the splitting is sometimes 10 to the power of minus 20 times the spacing between levels. So that's fairly unambiguous. I mean, if you're looking for, if you have a real physical problem where you're sort of on the edge of where tunneling is a small effect, then it might be a problem just to determine that from the spectrum. But you should be able to see from wave functions or anything else if you can calculate them.
I guess I still didn't quite understand the idea of sort of looking at kind of one orbit and varying each bar. For example, when I think of this distribution about the average gamma, I kind of think of it at one energy. The different quantum states correspond to all the different ways in the well that the energy might be distributed. Some modes and other modes and all mixed up, and when you kind of have all that whole ensemble of quantum states at roughly the same energy, but that's why you get a real distribution at about the average, because these different states couple to the tunneling coordinate differently and so forth. So I guess that's when you kind of, maybe I'm missing something.
Okay.
You pick kind of on one particular periodic orbit, and then you say you vary some other parameter to get a distribution, but it seems like you're always looking at one type of quantum.
Yeah. I mean, in a sense, we're not doing anything deeply different from that, okay? So this is just something which allows us to do numerical simulations. So what you're saying, if I understand correctly, is that you're saying if I take a narrow window in the spectrum and look inside there, then the statistics is governed by a particular orbit and so on.
But I would say many different orbits, many different quantum states at roughly that same energy. And
But-
the distribution comes because they have different characters, randomly or not.
Yeah.
And therefore they couple, more or less strongly to the reaction coordinate, to the tunneling
Yeah.
coordinate. And that's why you got some big, some
Yeah.
small, and so forth. That sounds to me different.
But that's just what we're saying.
But I thought you were always looking at one particular orbit.
We're looking at one. We're looking at one tunneling orbit. So what's remaining constant in our calculation is what's happening underneath the barriers. We're keeping the barrier fixed, but we're looking at many different states in the wellhead.
But the many different states, I thought they were all from one periodic orbit.
No, we're looking at the wave function on one periodic orbit, but the wave functions can vary, quasi-randomly from one to the next. Okay, so we're looking at, if you like, properties of the wave function, one small part of phase space, but then we're going to successive wave functions. Those are changing completely because the energy redistributes for each of those cases.
When all the construction you described, the complex periodic orbits that go through the well, I don't see where you need any symmetry. But you said if you want to treat a double well situation, you need the symmetry. So why can't you describe unsymmetric double wells with complex trajectories that go through the very?
You can, except then the effect is just a small shift in the energy level. And if you don't start off with near degeneracies, you get a tiny exponential shift in the energy level, and it's not really physically important. You want something where you can see these really small effects, but see them directly.
Practical reason. It's not a fundamental obstruction to the relation.
I'm not confident I can do the semi-classical calculation for asymmetric wells, because part of the thing you do with a double well is you use the symmetry. The problem is these exponentially small effects are hidden behind lots of H-bar corrections. When we do this, we sort of do something where we cancel off all the leading order stuff using the symmetry to get the exponentially small effects. With an asymmetric well, I'm not confident that what we're doing semi-classically would be valid.
So the energy shifts are the square of the tunneling amplitude,
Yeah.
like gamma, but
Yeah.
it's not just the amplitude.
Yeah. I mean, I think what we're doing, we should be able to state it in that way, but I haven't ever tried to, because it's in the calculations we're interested in, we can use symmetry to make the argument cleaner.
Even in an asymmetric well, the wave functions, you can tell better wave functions in the test.
Yeah.
Your harmonic oscillator ceases.
Yeah.
You implying that the first term in that sum was like the Heller-Kaplan.
Yeah.
So when you did the homoclonic orbit construction, were you only really dealing with the lowest term?
No, they're no. When you do, okay, so you're referring to something extracurricular, but yeah, if you include longer real-time evolutions and look at longer trajectories, those involved trajectories which are moving away from the central orbit, and you need this extra information corresponding to the higher states. I should point out that there is in practical terms, a limit where what we're doing reduces the Kaplan-Heller, which is that everything we do depends on a parameter lambda, which is the eigenvalue of that symplectic matrix. If that tends to 0 or its inverse tends to infinity, then the leading state dominates, and then it reduces the projection onto one wave packet. Okay, so what I'm talking about, where we look at collective properties in this complete basis, is valid when lambda is not 0.
The last one.
Yeah, and at the very end you show a few things that didn't seem to have anything to do with tunneling. So you showed the cat map and you showed the cardiac billion, and you told us scars are wonderful. Where did they come from? I mean, it had nothing to do with tunneling. So what?
No, okay, so the statement is scarring affects tunneling, but then what I'm claiming is that the sort of techniques used to explain this tunneling, this collective statistics, might be interesting in their own right.
So you just use a little pocket in the phase space and periodic orbit and goes through. That's the idea.
Yeah.
Thank you again.